Usually when we talk about space infrastructure, the imagery that comes to mind is, well, it's inherently aggressive.
Yeah, very much so.
You picture these multi-ton, gleaming metal fortresses being, blasted into a vacuum on top of controlled explosions. It's an entire discipline built around brute force.
Right. Heavy shielding and survival.
Exactly. Survival in the harshest environment imaginable. But welcome back to the Dump Dive, especially to you, the learner. Because today, we are unpacking a technological leap that completely shatters that mental image.
It really does. It's a total paradigm shift.
We are looking at a future where we abandon massive, dominating physical objects in space in favor of something almost imperceptible, invisible relationships.
Yeah, it is a complete inversion of the foundational logic of the space age. We're moving from a paradigm of isolated, armored strength to a paradigm of distributed agreement.
And the groundwork for this shift is mapped out in a truly fascinating piece of research. It's titled The Synchronized Swarm, Architecture of Distributed Agreement.
Yes, and this comes to us from a research team led by Associate Professor Atsushi Shirane.
Right, out of the Laboratory for Future Interdisciplinary Research of Science and Technology at the Institute of Science, Tokyo.
That's the one. And to set the stakes right up front for you listening, this is not just theoretical whiteboard math.
No, not at all.
They successfully proved the underlying technology at the 2026 IEEE International Solid State Circuits Conference.
Okay, let's unpack this. Because to really understand why Shirane's breakthrough is such a massive disruption, we first have to, dismantle the legacy approach to orbital engineering.
We have to talk about the hero object.
Yes, the era of the hero object, which the source material goes into. What exactly is that?
So the hero object is a highly accurate descriptor for how our global telecom network has operated for the last, 60 years.
Right.
We rely on monolithic satellites. We are talking about objects the size of a school bus.
Weighing several tons.
Exactly, and costing hundreds of millions, sometimes billions of dollars to design, construct, test, and finally launch.
It's a massive investment.
It is, and the entire engineering philosophy is built around heavy armor and internal redundancy. Because space is just an incredibly hostile environment,
Filled with extreme radiation.
And wild thermal fluctuations. So you over-engineer this single massive object to survive all of that.
I like to think of it like hanging an incredibly massive, terrifyingly expensive chandelier in the center of a pitch-black ballroom.
Oh, that's a good analogy.
Right. It is the absolute pride of the room. It holds all the intricate wiring, the heavy glass, the glowing bulbs that provides all the light.
But it's just one object.
Exactly. It's a single point of failure. If the main chain holding it up snaps, or if just one vital internal power bus burns out,
the whole thing comes down.
That multi-million-dollar chandelier crashes to the floor. The entire room goes completely dark in an instant. And that is basically our current satellite network.
Yeah, you have concentrated all of your functionality and really all of your financial risk into a single, highly vulnerable locus.
Which seems so risky.
It is. Because if a piece of orbital debris the size of a marble hits the wrong panel of a hero object, or, say, a single critical relay frise, due to a solar flare.
You lose the whole investment.
You lose it. And more importantly, a massive sector of global communications or GPS functionality just goes dark.
So the team at the Institute of Science Tokyo recognized that the physical size and astronomical cost of these monolithic models are absolute limits. We cannot just keep building bigger chandeliers.
Right. There's a ceiling to that approach. So they proposed what they call spatial wireless combining and distributing technology.
Which sounds very technical, but it basically means they want to replace the single monolith with thousands of synchronized Pico-Satellites.
Yes, and the prefix Pico does a lot of heavy lifting there.
We aren't talking about school buses anymore.
No, we are talking about incredibly tiny, cheap, almost disposable individual units. They're roughly the size of a Rubik's Cube.
A Rubik's Cube, that is wild.
And they weigh practically nothing. Now, on their own, they are severely power constrained. They have tiny solar arrays and extremely weak transmitters.
I mean, they'd have to, given the size.
Right. But the application of Shirane's technology allows thousands of these Pico-Satellites to collectively form a swarm. And that swarm transmits high-quality data directly to standard smartphones right here on Earth.
Completely bypassing the staggering cost and the launch bottlenecks.
And the vulnerability limits of the giant monolithic models.
Okay, here's where it gets really interesting, because I need to push back on the physics here a bit.
Sure.
This is where the concept sounds a little bit like magic to me. If you were telling me that one of these Pico-Satellites is virtually useless on its own,
Basically, yeah.
like its transmission power is roughly equivalent to a home Wi-Fi router, how is it getting high-quality data down through hundreds of miles of atmospheric interference to a standard smartphone antenna in my pocket?
It's a fair question.
Because even modern low-Earth orbit constellations, they require users to install a dedicated, pizza box-sized receiver dish on their roof just to catch the signal.
Right, a massive metal structure.
Yeah. So how is a weak Rubik's Cube-sized box hitting my phone directly?
So that is the exact mental hurdle that makes the 2026 IE paper so revolutionary. We are conditioned to think of hardware like the physical size of the amplifier or the dish as the source of power.
Right, bigger dish, bigger signal.
Exactly. But the researchers proved that the power doesn't need to come from the physical hardware, it comes from constructive interference.
Constructive interference, okay.
When thousands of these Pico-Satellites transmit, they don't just blast out noise independently, they perfectly align their transmission waves.
Wait, so the peaks and troughs of the radio waves literally stack on top of each other in the vacuum of space?
Yes, exactly. When the peak of one wave perfectly matches the peak of another, the amplitude doubles.
Oh, wow.
And when thousands do it, the signal amplifies exponentially without requiring a massive power source on any single satellite.
So it's like a localized network of shared intent. The swarm itself acts collectively as a giant phased array antenna.
That's exactly it.
Let me break down the phased array concept for you, just in case, because it's vital here. Traditional antennas, like a radar dish on a ship, they have to physically rotate to point a beam of energy in a specific direction, right?
Great. They mechanically turn.
But a phased array antenna doesn't move at all. It's a flat grid of hundreds of tiny transmitters. And by delaying the signal from certain transmitters by just a few picoseconds, you can shape and steer the combined wave.
It's highly precise.
It's kind of like doing a stadium wave.
Yeah.
If everyone stands up at the exact right microsecond, you create a directional ripple that sweeps across the crowd. The wave moves, even though the people just stood in place.
That's a great way to visualize it. And historically, we have only been able to build phased array antennas as solid physical objects.
Because they have to be wired together.
Exactly. All those tiny transmitters had to be wired into the same motherboard, sharing the exact same physical clock to ensure their timing was absolutely flawless.
But Shirane's team took the phased array and just blew it to pieces.
They did. They put each tiny transmitter on its own separate pico-satellite floating freely in space.
So the massive physical antenna isn't a piece of metal anymore.
Yeah.
The antenna is the empty space between the nodes. The relationship.
Exactly. But that brings up a massive technical challenge.
Well, yeah, because if they're physically disconnected, flying through a vacuum at, 17,000 miles an hour, this creates a massive synchronization problem.
A huge one. Constructive interference requires phase alignment down to the fraction of a millimeter.
And at low Earth orbit speeds, orbital drift alone would change the distance between the satellites constantly. Not to mention the Doppler effect.
Right. As they move relative to Earth and to each other, the frequency of their signals would shift.
So if their timing is off by even a nanosecond...
constructive interference instantly becomes destructive interference.
Right. They wouldn't amplify the signal. They would actively cancel each other out.
Yeah.
Resulting in just dead silence.
Dead silence. Which is why keeping the clock synced without a hardwired connection is the core problem.
How on earth do they do that?
That is precisely the engineering bottleneck that kept this in the realm of science fiction until now. Maintaining phase coherence across a swarm of violently fast, disconnected objects is incredibly complex.
I can imagine.
The breakthrough presented at the Solid-State Circuits Conference relies on a highly specialized mechanism involving a subcarrier frequency.
A subcarrier. So they aren't just transmitting the data, they are transmitting a metronome.
That is a brilliant way to conceptualize it, actually, rather than each pico-satellite relying on its own internal clock.
Which would drift.
Right, which would drift due to thermal changes in relativity. The swarm shares a continuous, low-frequency wireless subcarrier. It acts as an underlying heartbeat.
Oh, wow.
So every individual node listens to this heartbeat to calibrate its local oscillator.
And because they are constantly receiving this shared rhythm, they can dynamically adjust their phase delays on the fly.
Exactly.
They don't need to know their exact GPS coordinates down to the millimeter. They just need to calculate their relative distance to the rest of the swarm based on how long the heartbeat takes to reach them.
Which requires an immense amount of localized processing. Each Pico-satellite is constantly analyzing the subcarrier, calculating the Doppler shift caused by its specific trajectory, and then applying a predistortion to its own data signal. It shifts its phase so that by the time its specific wave reaches the target on Earth, it perfectly aligns with the waves from the thousands of other satellites.
That is insane. The physical metal of any individual unit is completely secondary to the precision of the synchronization.
It really is. The hardware is just a vessel for the math.
It's an incredible engineering flex. We're taking a single, heavy, vulnerable piece of hardware and replacing it with a localized network of pure mathematics.
To go back to your chandelier analogy, we aren't replacing it with a better, stronger chandelier. We are taking 1,000 tiny LED bulbs, throwing them into the air,
and programming them to flash with such perfect microsecond timing that they project a concentrated laser beam directly onto a single table.
Exactly. And that beam only exists because of their flawless cooperation.
Furthermore, that cooperation creates an unprecedented level of resilience, doesn't it? Let's look at the failure state of this system versus the hero object.
Okay, let's compare them.
If a micrometeoroid hits our multi-ton legacy satellite,
the entire network fails. The chandelier drops.
But if a micrometeoroid tears through the swarm and vaporizes 50 Pico-satellites,
nothing happens to the network.
The swarm just keeps flying.
The remaining thousands of nodes detect the missing signals, recalculate the phase delays, and the stadium wave continues uninterrupted.
Wow.
The relationship survives the destruction of the individual components. You completely eliminate the single point of failure.
So what does this all mean? This forces a pretty intense look at how we design systems in general.
It really does.
And the source material actually devotes time to these broader implications. It delves into what it terms the architecture of empathy.
Yes, that's a key part of the paper.
And I want to spend some time exploring that because it's a fascinating biomimicry parallel. When you look at human engineering, we have historically idolized brute force.
We build big, strong things.
Right. You see it in our power grids, our corporate software, our city planning. Everything is about building the most indestructible, dominating, centralized hub possible. We build thick walls and heavy shielding.
We armor everything.
Exactly. Yet our most bleeding-edge orbital telecom technology is now relying entirely on the opposite. Perfect synchronization, active listening, and distributed load bearing.
It challenges the very definition of structural strength. In nature, swarm intelligence is ubiquitous.
Oh, absolutely.
Look at a murmuration of starlings evading a falcon, or a massive school of fish moving as a single fluid entity.
Right, they move so perfectly together.
And these biological systems don't survive by evolving thick armor or consolidating into one massive organism.
Like a giant fish.
Right. They survive by being hyper-connected, individually agile, and constantly responsive to the telemetry of their immediate neighbors.
They survive through relationship. And that totally flips the script on how we view vulnerability.
How so?
Well, under the legacy hero object model, being fragile is a terminal liability. It's a weakness that you have to spend billions of dollars to armor against.
Right.
But in Shirane's swarm model, the extreme fragility of a single Pico-satellite is mathematically irrelevant. It genuinely doesn't matter that an individual node can be destroyed by a fleck of paint moving at orbital velocity.
Because the strength of the system isn't held in the physical object.
Exactly. The vulnerability of the individual is entirely absorbed by the redundancy of the distributed network.
And you can apply that architectural philosophy to a terrestrial challenge, like, say, a national power grid.
Oh, that's a good example.
Historically, we build massive centralized power plants. Hero objects.
Right, and when an extreme weather event takes down the main transmission lines?
Millions of people lose power instantly. The system is rigid.
It's the chandelier again.
Yes. But if we shift toward distributed agreement, thousands of localized microgrids, solar roofs, and neighborhood battery storage units.
All perfectly synchronized.
Exactly. Capable of dynamically sharing the load, then the destruction of one node doesn't trigger a blackout. The network just routes around the damage.
Because the network is constantly listening. And that is the core requirement of the subcarrier technology we discussed earlier.
Active listening, yes.
To maintain that perfect phase alignment, these Pico-satellites cannot operate in isolation. They have to be constantly aware of the state of their neighbors.
Right.
A system that operates like a synchronized swarm is a system that demands constant communication and mutual recalibration, rather than just rigid top-down commands.
The technical term is dynamic fault tolerance, but the social parallel is undeniable.
It really is.
A monolithic architecture assumes that the environment can be conquered with enough shielding. A swarm architecture assumes that the environment is inherently unpredictable.
And that survival requires constant adaptation and collective support.
Exactly. And as this spatial wireless combining technology matures, it will likely drive down the cost of global internet access by orders of magnitude.
Which is huge.
You won't need to build massive launch vehicles just to get a communications array into orbit. You can pack thousands of these Pico-Satellites into the payload margins of other missions.
Which fundamentally democratizes space infrastructure.
Totally.
If the cost of entry drops from billions to millions, it isn't just massive nation-states or megacorporations that can deploy a telecom network.
Right, research universities could do it.
Smaller nations, independent organizations, they can launch their own synchronized swarms. The hurdle shifts from, can you afford the rocket fuel to lift a school bus, to, can you write the software to keep the swarm perfectly synced?
It moves the power from heavy manufacturing to algorithmic precision.
And it solves the ground infrastructure problem entirely.
Oh, definitely.
Okay.
By effectively turning the orbital swarm into a massive, highly directional aperture, you put all the energy burden on the transmitter.
So the receiver on the ground, like my standard smartphone, doesn't need to do any heavy lifting.
None at all. It just receives a perfectly concentrated signal as if it were standing next to a cell tower.
Even though the tower is a decentralized cloud of metal cubes flying hundreds of miles overhead at Mach 22.
Exactly.
It is a profound shift from hardware to harmony. To bring this all together, our deep dive today started by looking up at the massive, vulnerable hero objects that have dominated orbital mechanics for decades.
Then we explored how Associate Professor Atsushi Shirane's team at the Institute of Science Tokyo solved the immensely complex physics of spatial wireless combining.
We detailed how a subcarrier heartbeat allows thousands of fragile Pico-Satellites to constantly recalibrate their local oscillators.
Overcoming orbital drift and Doppler shifts, yes. By achieving perfect phase alignment, they create constructive interference.
Effectively forming a giant virtual phased array antenna right in the vacuum of space.
We saw how the physical constraints of heavy metal and massive launch vehicles are being replaced by invisible mathematical relationships.
Proving that immense power and resilience can be generated through distributed agreement rather than brute force.
And finally, we explored the architecture of empathy, the realization that biomimicry and swarm intelligence offer a more resilient blueprint for complex systems than the rigid single point of failure models we have historically relied on.
I want to thank you for joining us on this deep dive today.
Yeah.
This isn't just a story about how you might get better cell reception in the middle of the ocean 5 years from now.
No, it's much bigger than that.
It is a fundamental reimagining of where strength actually comes from. So as you go about your day, I want to leave you with a final thought to mull over, one that brings this concept all the way down from low Earth orbit and into your own daily life.
Let's hear it.
Look at the systems around you today, the way your workplace is structured, how your community handles a crisis, or even the way you attempt to solve your own personal challenges. Are you still exhausting your resources trying to build an indestructible, heavily armored hero object to carry the entire load? Or is there a way you can let go of the heavy metal, distribute the weight, and find your true resilience in the invisible, synchronized agreement of a swarm?